Every second, without thinking, you do something no machine has ever fully replicated. You walk. What seems effortless is actually a cascade of thousands of micro-decisions. Bones loading like springs, muscles firing in milliseconds, forces rippling through 206 bones and over 600 muscles, all synchronized with breathtaking precision. To truly understand what's happening, scientists are pointing high-speed cameras, capable of capturing over 1,000 frames per second, at the human body. What they're finding is extraordinary. Locomotion is simply how organisms move from place to place. But human locomotion, bipedal gait, is something special in the animal kingdom. Most creatures use 4 limbs for stability. We evolved to use just 2. Around 4 million years ago, our ancestors shifted from knuckle walking to upright striding, freeing our hands and transforming our spines, hips, and feet in the process. This evolutionary trade-off came with costs: lower back pain, difficult childbirth, but the payoff was extraordinary cognitive and cultural development. Understanding how we walk means understanding one of the most significant adaptations in evolutionary history. Every complete stride you take is called a gait cycle. It has 2 major phases: the stance phase, when your foot contacts the ground, accounting for roughly 60% of the cycle, and the swing phase, the remaining 40%, when your foot is airborne. Within the stance phase, the gait cycle begins with heel strike, the moment your heel contacts the ground, then mid-stance, when your full body weight loads over the foot, then toe off, the powerful push that propels you forward. During normal walking, there's a brief period, called double support, when both feet are on the ground simultaneously. Fascinatingly, if you eliminate that double support period and increase swing speed, you transition from walking to running. It's not just faster, it's a completely different biomechanical pattern with fundamentally different force profiles and energy storage strategies. To analyze all of this, scientists need tools that can freeze time. Enter high-speed cinematography, cameras capable of recording at 1,000 to 10,000 frames per second. At 1,000 FPS, a heel strike that lasts just 50 milliseconds can be stretched into over a second of analyzable footage. But capturing images alone isn't enough. Optical motion capture places retroreflective markers, small, shiny spheres, on anatomical landmarks across the body. Infrared cameras triangulate each marker's 3D position dozens of times per second, building a precise digital skeleton in real time. Modern systems combine this with inertial measurement units, or IMUs, tiny gyroscopes and accelerometers embedded in wearable suits, allowing motion capture to move outside the laboratory and into the real world. Together, these tools transform invisible movement into precise, measurable data. Every time your foot hits the ground pushes back, and this is Newton's third law in pure biological action. These ground reaction forces, or GRFs, are measured using force plates, embedded sensors in the floor that detect magnitude, direction, and point of application of every force your body exerts. During walking, your GRF profile shows a characteristic double hump curve. The first peak at heel strike, roughly 110% of your body weight, drops into a valley at mid-stance, then rises again to a second peak at toe off. When you run, those peaks can exceed 250% of your body weight, reached in under 50 milliseconds. Your body absorbs this through a brilliant cascade of yielding joints: ankle dorsiflexion, knee flexion, and hip loading, all acting like a biological suspension system, protecting your bones from fracture with every single step. While force plates tell us how much force is involved, kinematics tells us how the body moves to manage it. Researchers track the angular motion of every major joint throughout the gait cycle. At heel strike, the ankle is nearly neutral. It then dorsiflexes, bending upward, through mid-stance, absorbing load, before plantarflexing explosively at toe-off, generating forward propulsion. The knee flexes to about 60 degrees during the swing phase to clear the ground and unfurls for the next contact. Meanwhile, The hip extends powerfully as you push off, then flexes to swing the leg forward. And orchestrating all of this? Electromyography, or EMG, sensors that detect the electrical signals your nerves send to muscles, reveals the precise timing of muscle activation. The vastus lateralis, gluteus maximus, tibialis anterior, and gastrocnemius fire in a meticulously coordinated sequence, a symphony conducted by your spinal cord at millisecond precision. This knowledge isn't just academic. Biomechanical analysis is reshaping sports science, helping elite athletes optimize stride efficiency and reduce injury risk. It's guiding the design of advanced prosthetic limbs that replicate natural gait patterns. It's informing rehabilitation protocols for patients recovering from stroke or orthopedic surgery. And perhaps most ambitiously, it's teaching engineers how to build bipedal robots, machines that can navigate human environments with the elegance and stability we take for granted every single day. The next time you take a step, remember, you're performing one of the most sophisticated feats of engineering on the planet, refined over 4 million years of evolution, and we're only just beginning to understand it. If this video sparked your curiosity, subscribe for more science that makes the invisible visible. Drop a comment below. What aspect of biomechanics would you like us to explore next?